Okay, different topic today. FSM encoding is an important step that takes us closer to hardware detail from the behavioral level of abstraction. If we look at the output of high level synthesis, there was this data path which looks very structural, right. This part of it is closer to a netlist, whereas this part is still symbolic as of now, okay, nowhere close to a netlist. So, we need to do something about it. That is what this FSM encoding is about. It is also variously called state encoding, state assignment and so on, all of them referring to the same problem. What is the problem? We assign codes to symbolic states in an FSM. These are the symbolic states S1, S2, S3. We can name them whatever, usually you choose some meaningful name for the states. This is a Mealy machine, we understand this annotation, right. 1 0 refers to the condition and this 0 0 here refers to the actions. We need to assign codes to the symbolic states, so that no two states should have the same code, that is the objective. What does the encoded FSM look like? If this is the original FSM, the encoded FSM would be different in what way? What do we mean by assign codes to symbolic states? Yeah, so what do we do to this FSM to encode the states?
Some binary code.
Yeah, you replace these symbolic names with some codes, right,
So
0 0
variable
0 1.
In a way, at HLS level, it will be seen as a signal or a variable with a certain size as the bit vector.
Yeah, so there are some decisions we need to take as part of the state encoding. The length of that bit vector is one of them, but of course, what is the value that we give to each state is the other one. That is a state encoding problem. This is just a specification of what we do. There is the question of an optimization function. What should be optimized as a result of this action? Clearly, there are many different choices for state encoding. So, that is the FSM encoding problem. Let us define the optimization function a little later, but first let us understand that there is a diagram that is used for illustrative purposes. Equivalently, one could look at the FSM as just a state table. These two things on the left and the right, these two representations on the left and the right, they are equivalent. So, I have the input part and that is the output part of the state table. We have these columns in the state table that refer to an input section, a present state section, a next state section and an output section. How many columns do I have? The inputs, this refers to the number of inputs, assuming these are all single bit, number of inputs I have. Present state, that is the state, next state is also the state. Outputs, again there will be as many bits on the output side as there are output bits in the FSM. These two are identical, they contain identical information. Every row of the state table corresponds to what in the FSM diagram? A transition. If I say on 1 0, I transition from S1 to S2 and in the process the output is 0 0, I should be able to tie that to a row where I have essentially captured the same information. Condition is 1 0, S1 to S2, that is the transition and the output is 0 0. So, for every transition that I have, I can expect a row that is capturing the same information. So, it is the same thing, FSM is fine, the diagram is okay from a visualization point of view, but from an automatic processing point of view, clearly that state table is something that will be useful. So, why do you encode the FSM?
Differentiate between the states.
So basically in hardware everything is 0 1, so you have to assign it to a variable some. Now what values to choose?
In the process of implementing it, somewhere that symbolic name needs to be translated into zeros and ones, so that I could realize whatever the logic is in terms of some gates. Right? And gates understand only zeros and ones, so that is the need for the motivation for encoding it. First question is, how many bits should I have in that encoding? That bit there is relevant because we know the standard template, right, how that logic looks like, the hardware looks like that would implement a particular FSM. Every bit in the state encoding translates to what? Or a longer or a shorter encoding length has what implication on the hardware that is inferred?
Please repeat the question, sir.
I have to answer this question, how many bits will I use for representing a state? Encoding means I have to assign a bit stream, right, for each of them 0 0 or 0 0 1 and so on. How many bits should I use?
Log 2 of number of states. Log of number of
I take the number of states, and the minimum I need is the number of bits that are needed to at least get so many distinct numbers. That is the logarithm to the base 2 of the number of states. So, you take the ceiling because it is an integer that we need. Why do we use that? Could I have used a longer state register that translates to, but why did you took the minimum, but was that necessary to take minimum? More storage will be required. Yes, each bit translates to a flip flop. Right. It is a state register that I found that consists of a number of flip flops, and if I use 2 bits, then I have 2 flip flops there. If I have 3 bits, then I have 3 flip flops. So, of course, there should be an attempt to minimize the number of flip flops, that helps in some way, but if I had an area metric for optimization, I will try to minimize the number of flip flops, and therefore, I try to use the minimum length encoding here. Okay.
So what is the other trade off of using minimum length?
I will get to, we have not defined the optimization function yet. So, maybe we postpone that discussion. Okay. So, when I do this encoding, right, S3 becomes, so I just replace the occurrences of the symbolic state by the respective encoding. All these S3s are replaced by all the equivalent codes. Then I have essentially what is a truth table. Okay, what you see here is a truth table. What can I do with a truth table? Now that it is in this representation, what is the next step? Ultimately, I want to generate hardware out of this logic. This somewhat represents the combinational logic that is involved. Right. What is the next step after the truth table? You can generate gates out of this. This truth table is nothing but the equivalent of a Carnot map or whatever, right. All the bits are there, all the don't cares are also nicely specified. So, I can proceed with my logic optimization and realization of a gate level netlist from that truth table, of course. The architecture may be illustrated like this. I have a state register that captures the current state of the system. What is there in the state register?
the flip flops.
The flip flops. It consists of only the flip flops, nothing else. And if I have a 2-bit encoding, then that state register will have 2 flip flops. The standard representation is you just assume it is a D flip flop. So, that whatever the next value is going to be, that is what is computed in the logic here, and that goes as input at the D input of the flip flop. And what you see here, these are the Q outputs of the flip flop. Those are fed back into that same combinational logic, and they become the present state, right. That computation here is the next state computation that goes into the D flip flop. That is essentially preparing the data for the next state. That is the architecture. This combinational logic consists of 2 parts. There is a next state logic and an output logic. Of course, all of these are the output parts, right. So, these are computed, the inputs are these. So, these are input, the inputs and the present states are these inputs to the next state logic. These 2 consisting of the present state, where those are the Q inputs, and these are the external inputs into the FSM. What are the outputs? There are 2 output sets. One is the external output. From a HLS output point of view, you can see that these are the control signals that go from the FSM into the data path. The other set of outputs are these are the next state outputs. So, that combinational logic is all of this. That is essentially a translation of this logic that is specified here in the truth table. That is the overall flow and the hardware architecture we are assuming. Any questions on just the overall picture? We will get to, then the question is, how do you take that decision? That S3 translates to 1 0, what is the basis and how do you take that decision? That is the FSM encoding problem, but it is embedded in the bigger problem, that is this. Okay, I have to actually specify an objective. By itself, it is hard to argue that one encoding is better than another encoding. You have to say in terms of what is it better. So, our objective is the translation is from a state table into a truth table. That truth table can then be optimized using standard logic minimization techniques. So, we should hopefully be familiar with the basic ideas, but we will talk about this in the next step. But I have to specify an objective, and for now let us say that the objective is to find an encoding that minimizes the area of the final circuit. What is important to note here is that as part of this encoding step, we are not generating the circuit. We are only anticipating what will happen later. Encoding in fact is just this. You take the symbolic FSM and perform just these encodings, so that you get this truth table, that is all. But it is hard to see at this level why one would be better than the other. So, somehow you have to argue in terms of what happens later. If I take this decision, then the later logic optimization step can benefit in this way or that way. That kind of an indirect argument has to be made as we make the choices for the encoding. This is not so trivial, and there is a lot of dependence on what the target architecture looks like. How are you going to implement that FSM? We did have a truth table representation. Truth table is also a high level representation. It is only a specification of the functionality of the logic. You can say that you will use an array logic kind of a target, in which case there is some such construction. Are you familiar with what a programmable logic array looks like? So, it could be this kind of a target. As you know, there would be an AND plane and there would be an OR plane. In that AND plane, you would be generating, what are these? These are the inputs to my system. These are the outputs. It is combinational logic that that PLA actually ultimately implements. I have a couple of flip flops here outside, That is my state register, and these actually go back over here forming the inputs, that is essentially the present state, right. And these outputs here are the next state computations, and these other outputs are the external outputs of the FSM. So, that is the implementation. So, what would these be? That this, well, each of these, what is the meaning in this implementation? What we are saying is, if you had the input variable, if this was x, then this is x prime, right, x bar. If this was y, then this was y bar. So, such a connection here in that AND plane means what? Means you select these are, what are these? Rows mean what and columns mean what in the PLA? Let us say initially just in the AND plane, there we have introduced a connection there, that is the programmable part of this logic. I have to decide how to program it, and programming it essentially means that I decide on those connections, which connections should be there and which ones should not be there. I introduce these two connections to mean that this line has some logic. What is that logic? So, I selected x and I selected y, the AND of those is what that line there represents. Similarly, I selected all these 3 here for the next row. So, that would refer to x prime, y is not there, and if these present state lines you call them whatever a and b, then a is there and b is there. So, that is the meaning, and so terms are formed, product terms are formed, and you select from the AND plane of the PLA which lines you want, and the complemented versions are also available, so that we can form any expression. So, but these are all individual terms, AND terms. There may be as many literals, as many variables here as the number of connections you make there. So, that is what these are. What is there in the OR plane? Yeah, the columns there represent what? That these so if I call them A and B, let us say this is A prime and this is B prime, then if I have chosen these two, it means that x and y is what is selected. So, x y is one AND term and this is the other AND term corresponding to x prime a b. So, that is x prime a b, and through selecting both of them we mean that that output line here it is actually a next state line is this term, this product term plus this product term. So, in the AND plane the horizontal lines are used to compose the product terms. In the OR planes the vertical lines are used to collect the appropriate product terms to form whatever expression we want. That is if the target was a PLA. It could also be that I have multi-level logic. The PLA is an example of a 2-level logic structure. You have AND terms and OR of appropriate AND terms, nothing more than that. There are only 2 levels, but you do not have to do it that way. You can have any number of levels. So, that is one level, this is another level, this is a different level. So, in general, of course, nobody is stopping you from having any number of levels, but that target architecture is different. You could have a standard cell based architecture where you pretty much have random logic and you can implement any number of levels. If you use one of those predefined architectures like a PLA, you are constrained with respect to what kind of expressions you can implement there. This target architecture has to be specified to the FSM encoding strategy, because the way you would encode even if it is for minimum area, the way you would encode if the target architecture were PLA or an FPGA for example, may be different from the way you would optimize it if it is multi-level logic and ASIC library is used to implement it, standard cell library is used to implement it. That needs to be specified. So, let us identify what do you need to optimize. If I say area is our target to begin with, then what should you optimize? In the PLA implementation, what do we optimize?
Number of connections.
Number of connections. What difference does that make in the?
I can put more logic in the same area.
The number of connections, would it have an implication on the area of the PLA?
No.
No. So,
Area of the logic.
so that is the area, right. This is my area that I would like to minimize. What is actually available in my hands?
You can put a bigger logic. I mean, efficient utilization of the resources.
Let us assume that we are going to construct a PLA that implements our logic. FSM is there, I need to realize it in terms of a PLA. So, I am looking for the smallest PLA structure that would that would be good enough for our logic. So, what does that translate to? What do I actually need to optimize here in this picture in order to minimize the area of the PLA? First, what is a very high level model of the PLA area? This is a rectangular structure, right. Its area is determined by length and breadth. That is a great beginning. Length here translates to what and breadth here translates to what? Number of rows and number of columns. That is a great improvement upon refinement upon the abstract idea of area of PLA. What determines the number of rows? What determines the number of columns? Number of inputs, just number of inputs? Number of columns is what here? You determined by what things? Number of inputs and number of outputs also, because those are also occupying space, right. There is a column dedicated to every output. So, these are determining the number of columns. Number of rows is determined by?
The number of expressions we add.
Number of minterms.
Can you be more precise? What is a minterm? If you have a logic of 4 variables, what is an example minterm?
You can't break it down further beyond what it is.
So, give me an example minterm.
Like all 4 terms will appear in that.
All the variables will appear in every minterm, either complemented or uncomplemented, but they all appear. That is the minterm definition. This is a minterm. This is not a minterm. So, now can we get back? What determines the number of rows in the PLA?
The number of minterms in the expression.
Total number of.
Not number of, in this expression has how many minterms?
1.
No.
Sorry.
This is a product term. In general, this is a product term that actually corresponds to 4 minterms, the sum of 4 minterms. Right. What we want to minimize here, if I want to minimize the number of rows, is the number of distinct product terms I am using in composing these expressions. Distinct because I may actually reuse some product term. I use it here. There is this is a product term that is available for me for use in any of these output lines, right. So, this product term has been used once for that output, also once for this output. So, I do not count that twice, because that line is available to me, it does not constitute additional area. In this kind of a technology, the number of connections are irrelevant. If you look at the layout, this may be done, I mean this is actually part of a pre-designed structure. Establishing a connection or not establishing a connection does not add or subtract area. The way these are designed, you would turn some metal on or off, either connect some line to voltage 1 or like an input gate to a transistor, either you say you connect it to 0 or a 1, but the transistor is already there. Right. So, you are not saving that. Those are the properties of structures, regular structures like these. Okay. So, if I were to now minimize the area of this PLA, one thing is I should try to reduce the number of distinct product terms I use. That reduces the number of rows. What can I do about the number of columns? Clearly, I have some flexibility in choosing this, because depending on how my logic looks like, I may have more or less product terms. Here, in terms of the number of columns, what flexibility do I have?
As we discussed earlier, for the state register, if we use the minimum logic for that.
Yes, I have some flexibility here. If I use more bits, then I have more columns for the state register. So, if I just want to minimize area, perhaps I can just use the minimum number of bits.
Kind of problem, because if I use exploded state register, then my number of product terms can reduce. If I use less, then my distinct product terms can increase. So that's where the optimization angle comes in. Whether
What do
you
you mean by
optimize number of
exploded?
columns more or you optimize number of rows more, that is where the balance will
Yes,
come
we
in.
should understand the trade-offs here. Some of the choices interlinked. For example, the number of state bits. By itself, it does not say much, but it depends on how you are actually doing the encoding. It is possible that for some choices of length of the state register, the logic is simpler. You actually might need fewer product terms. Then since we want to optimize the product of the columns with the rows, there is some such uncertainty. But other than that, what are the column choices that we have? These output columns, I do not really have a choice, because they are going outside, those need to be there. What about the inputs? Inputs are fixed. Now, there is this question of, does the inverted input also need to be there or not. So, some choice you can say it is there. So, that depends on the methodology a little bit. You could optimize so that you could give preferences to those kind of expressions where either the variable or its complement is there, but both are not there. So, there is some such flexibility that is available, but in general when we talk about a PLA structure, we put both the x and x bar lines. So, there is really not much flexibility. Overall, not much flexibility is there in the choice of the number of columns other than the state register length. But this is the bigger dimension on which there is some flexibility, and we can make an encoding choice that optimizes the number of rows in the PLA. What if it was a multi-level logic implementation and I want to reduce area?
How are we going to implement multi-level logic? Simply gate structure.
Yeah, our implementation is just this. Let us assume that we can just pick up discrete gates and compose a circuit that looks like this. So, area optimization here translates to somehow minimizing the total area that is occupied by all the gates, the sum of the areas at this stage. How do you do that? That should also translate to something at the high level, like we argued in the other case that I want to reduce the number of product terms. That is taking us a little higher level, so that we can argue algebraically as we take decisions on the encoding. Here, what kind of argument it would be if I say I just want to reduce total area, that is total area of the gates. Can we translate that into something of an algebraic nature.
The standard logic minimization techniques can be applied to make.
Standard logic optimization techniques would indeed be applied after we perform the encoding. So, at this stage somehow we need to anticipate what happens there. Remember, we are not generating the circuit as part of encoding, we are not generating the circuit, we are only taking those decisions of the translation of the symbolic correspondence of the symbolic states to our distinct encodings. That is all that we are doing, but in the process of doing so we should anticipate what happens later. Number of gates is an interesting low level metric that one can try and anticipate. Often the proxy that is used at a high level for estimating the number of gates is the number of literals I have in an expression. Ultimately, there are some bunch of Boolean expressions that are generated, right, and our choice here for encoding has to be based on which Boolean expression is better. So, that means that I have some expression like this and I have some other expression maybe with the same result, maybe they are all equivalent logically to each other, but they are not all equivalent with respect to implementation if you were to later translate them. So, given an expression, we can do something to estimate its complexity that would translate to an area number ultimately. The measure that is often used is called literals. Literal refers to the presence or absence of a variable in an expression. Okay, so, if A is present, then I count once. If C prime is present, then too I count once. Why it is worth thinking about? If B and C, so this 2 is 2 literals, A prime B is also 2 literals.
The B has already been counted, so it should be 5 literals.
No, every time it occurs in the expression, a particular variable occurs in an expression, we still in any product term in an expression, we say that it is an additional literal. It is worth it or it is not worth it.
It's called literal count.
Yeah, so here literal count is 6 in this expression. Why do we do that? Or first of all, is it good to do that, or we should be counting only the number of literals? Number of literals anyway tells us what? It says something about the inputs that I have to the expression. We want to capture the complexity of the circuit that will ultimately be generated. So, a literal count is what we want to do here, but is it okay to count B twice the way it appears in the expression, or should we appear once as a measure, as an approximate measure of ultimately what should translates to gate count. Right. So, if I have this expression here B C plus A prime B. So, point is B occurs twice, should I count it twice? That is what this counting is doing. Let us be convinced that it is okay to do so. Maybe for now let us just ignore the prime here, that is a different argument. Why should we consider the variable and its complemented form as one literal each is a separate argument that we will come to, but for now let us just be convinced that counting B twice is okay in that kind of an expression.
Because we need 2 different gates.
It translates to an additional gate. It does not matter that it has occurred earlier. This is one AND gate, the other one is implemented using a different AND gate. Maybe there is an OR structure there. So, B may occur any number of times, but the argument here essentially is that every time it occurs, it has an impact on the gate count of the circuit. Right? That is the intuition, that is the reason for a separate counting of every occurrence of a literal. If you had another one, if you had plus ABC here, that you can separately optimize, it is a different matter. We aren't going this, let us say this is my ultimate expression and I want to translate that in a straightforward way later on into gates, then that ABC here indeed translates to a separate gate structure. So, we are saying that every time such a literal occurs, then that translates in some ways to an additional 2 input gate or whatever our minimum element is. Therefore, we count all of them, all those occurrences. Yeah.
If we just consider BC plus AB, that's B into C plus A. So
Oh,
it
no,
will be just 2
we are not
gates.
considering the optimization. We are considering that this is the final expression that we have, and I want to take that and build a netlist out of it. That there is a better representation of that expression, that there is a more compact representation of that expression. If it is there, then you replace it, and that is what we want to count. So, somehow this is the last stage of all the optimizations, and we want to evaluate how good it is without generating a circuit out of it.
So can we put it this way? For example, if I take a 2 input NAND,
Yeah.
then for each literal in that expression, I will be consuming one stack of P and N if it's a complementary
Yeah.
MOS implementation.
Yeah, yeah.
That's what it is.
That is what this translates to. It
That's why
translates to more area, and the equivalence here is it is like a 2 input gate or something like
Basically,
that.
that way you are able to cover the logic implementation details also in
Yeah,
one shot.
that is what we are trying to estimate. Every time something like this occurs here, it translates to 2 transistors in the logic implementation. Indeed, yeah, that is one. The other thing is our approximation that I have AC prime plus B prime C or some such thing. This is still counted as 4 literals. Are we justified in doing so?
Yes, sir.
Why? What about these 2 inversions?
An inverter has to be realized to invert a signal.
Right. So, I should count that or I should not count?
We should count.
Right. So, I have 4. So, I am taking this as equivalent to AC plus BC. If literal count is the only thing that we use as an approximation of the area, then both of these are equivalent, but you know that they are not equivalent because the 2 additional inverters are there. But still, remember, this is a high level approximation. Would we be justified? Would there be an argument for actually ignoring?
We can assume that complemented inputs are already available.
Yeah, it becomes a little tricky to capture these effects exactly. This is an approximation after all. The point is, you may have something like this, A prime, B prime. Now, compare this with AB, which is the more expensive circuit? This, because this translates to a NOR gate, right, whereas this is actually a more expensive circuit, and the realization consists of an NAND gate followed by an inverter. Right. That is why we get rid of this distinction. On an average, we ignore the complement. We just say existence.
Overall, global picture, things will normalize.
Right.
That's the
Right.
That's the
So,
case.
these are some approximations which are necessary. At a high level you need to make that. At a high level it is hard to, and without realizing it, right, it is hard to come up with a more exact picture. So, we just ignore those things. Although, if it is very simple, then you should be able to do something about it being more accurate with respect to that estimate. So, there are some limitations, but still overall the literal count is considered as a very nice proxy for the complexity of an expression when it comes to multi-level logic implementation. In the 2-level logic, for that PLA structure, would literal count be good?
So in the PLL structure, AND OR can be implemented very efficiently, and we have all the inputs available for us.
Right.
So literal count can't be.
The equivalent argument here would be, let us say you have some logic here that is represented by this picture, and consider the addition of an extra connection. That translates to one more literal, right, in the Boolean expression. Does that translate to more area? It does not. We just argued that the area is independent of the number of connections. In the multi-level structure, the area is dependent on the size of that expression. So, here we are dependent, the area is dependent on the number of product terms that are appearing. So, it is not as though there is no dependence at all on the complexity of the expression, but it depends in a different way, not merely because the size of the literal count is more or less. So, in this we do not use literal count, we would use product term count.
For a given set of inputs, we can have all the product terms and min terms that
Right,
we want.
right.
So that
Yeah.
doesn't make a difference. If we increase an input, then it will make a difference.
If you have an additional input, then it makes a difference because you have a more column. Yeah. Okay, so this is what we would try to optimize. If the target is a PLA implementation, then I try to optimize essentially the number of rows, which is number of product terms. That is a different optimization. If it is a multi-level logic implementation, then I try to optimize the gate count, and that gate count at the Boolean expression level, what we try to optimize is the number of literals in the expression that will be later built up. Remember, we are not going to build up these expressions, that is actually part of the logic minimization step, which comes later. But we try to anticipate what happens in that step as we argue about the state encoding. Let us see what options do I have for state assignment. I can use the minimum number of bits. If n is the number of states, then I take log n to the base 2, ceiling of that tells us the number of bits that are there in the state register. So, this kind of a choice can be made for the encoding, but of course, I have a large number of choices there, even if I use the minimum number of bits. So, that minimizes the number of flip flops. So, that is some step in the direction of optimizing area. But that is only one. The other extreme you might be familiar with is what is called a one hot encoding. I use as many bits as the number of states. So, that would mean that if I have 4 states, then I use 4 bits, and the encoding could be such that the corresponding bit is 1 and all the others are 0, or it could also be the other way around, which is all the other bits are 1 and for that state it is 0. So, this leads to more flip flops, right. For this example, it is 4 flip flops instead of 2, but it actually might simplify the logic. We just talked about it in the PLA context, but it may simplify logic. Why would it simplify logic?
So the next state derivations will simplify, your output derivations may also simplify depending on the expressions
Conceptually, so that logic has 2 components. The logic for determining the next state or the logic for determining the output has 2 components. One is which state are you in, and the other is what are the inputs, because those are my inputs there. Which state you are in, that part of the logic is a simpler implementation if you have one hot encoding. Why? Because you just pick up the appropriate bit, and that bit is 1 means that you are in that state. If it is 0, it means that you are not in that state. So, if you are looking for a particular transition from S2 to S3 and you want to know are you in S2, that logic is very simple in one hot, because you just pick up the appropriate Q output of the flip flop, and that being 1 or 0 tells you whether you are in that state. If it were the minimum bit encoding, then you would need a little bit of logic to tell you are you in this state or not, because it would be encoded as 1 0 0 or something, which means that you need 2 inverters and a 3 input AND gate to tell you that you are in that state.
If you encode, you have to decode.
Yes, there is a decode that is implied there. The logic may not be as explicit as this, because of course you are sharing logic all the time, but conceptually this is the argument, that there is an explicit decoding that has already happened as part of the one hot encoding step. So, logic could be simplified, which means that the area could be lowered. For the logic part, the area of the flip flop has increased, but the logic could possibly be simplified. But the more important is, this could possibly be a faster design, because the critical path is counted from flip flop to flip flop, right, Q output of the flip flop to the D input of the next flip flop stage. If the logic is simpler, then it is likely to be faster. So, there is some merit to one hot encoding also, and in general it is not clear which one you should use there. It may depend on what your objective for optimization is. Although the other thing to note here is that if you take it to the extreme, even 1 hot leads to complicated circuits. What if you had 500 states? Right. It is not an uncommon design where you have a large number of states. Right. So then we are talking about 9 flip flops versus 500 flip flops. Somewhere this argument ought to break down in terms of the implications later on with respect to layout. Right.
Can you explain why this will be faster?
Why is this likely to be faster? The reason is the same, because the logic may be simpler. So, in one case we have a 3 flip flop design. So, if whether you are in a particular state or not, you need to determine by let us say 0, say that is the encoding that we are looking for. So, the circuit is this. This tells you, are you in state S2 whose encoding is 001. This is not the only thing. In fact, there are maybe a couple of other inputs. These are the primary inputs x and y, and that transition could be that maybe you have an OR gate. If you are in that state and either x is 1 or y is 1, then the output is something. Let us say that is my logic. If I use a minimum width encoding of 3 bits, maybe my design had 7 states. So, instead of 3 flip flops, maybe I could have used 7 flip flops. And S2 corresponds to this, right, the 7 flip flops. If this is the Q output, if this Q output is 1, then I am in S2. In the 1 hot encoded version, that line tells me that I am in state S2. Okay. X and y are still there, and my logic could be this. Just getting this output tells me that I am in state S2. That is nice. This whole of this logic was avoided. That is the decoding logic of the state. That was avoided. I directly got this, and except the rest of it still remains the same. So, in the critical path of the design, we omitted a part of the logic. That is the simplification we are talking about. It could lead to lesser area, but that is a little trickier argument, because there is a counteracting increase in the area for the flip flops. But the speed argument is usually there, because that logic is now missing here, and this has a smaller critical path.
Encoding get complicated with 1 hot scheme.
The next state, so what is the next state logic anyway? Next state logic is also, if you look at the, so that is my input, present state, next state and output, right. So, just like an output logic look like this, the next state logic is, so this truth table is just a general truth table, zeros and ones are there everywhere. This could well have been one of those next state lines. Same logic. In order to find that the next state should be S2, what do you need to do? You need to check whether current state is S1 and the inputs are such and such, and that decoding is omitted in that logic also, because okay. So, each of those computations is smaller, but now you have more computations, because you have 7 lines going to the next states instead of 1.
Connections will increase, but not
Connections will increase. Each of them is simpler logic, but now you have more logic perhaps, right. The speed argument is still there.
speed can be
right, because each of the logic elements is simpler and therefore the critical path could be smaller, but the area is the trickier. I did not propose this as an area optimization, I only said this is possibly faster. Area is a more complicated argument, it is hard to argue.
Sir,
Yeah.
why do we need all 7 lines going forward? Because if we know that we are in state 2 and the next state is going to be state 3, we need only 2 lines. The state 2 should be set to 0 and 3 should be set to 1. All others are already 0 when one state 2.
This is the implementation of one transition.
Fine. What I'm talking about is like he was saying that when we are calculating the next stage, we need to send all 7 signals.
7 signals need to be 7 D inputs need to be given to the 7 flip flops, right. They would correspond to all those transitions where that particular state is the next state.
Okay. So, but the rest of the flip-flops can just sit in the previous
Rest
state.
of the flip flops do not change, it is true.
So even in the logic realization, we need only 2 lines from every state for calculating the next state. We need to set 1 to 0 and the other state to 1, that's it.
See this 7, these are the Q outputs of the flip flops. The input D values do need to be provided, right. How do I provide it? I pick up from these rows all the rows where let us say S3 is the next state. And build some logic like this. Let us say there is an OR gate or AND gate and so on, some combinational logic. Any one of them is 1, then my S3 should be 1. So, that comes from perhaps an OR gate that is picked from many different parts. So, every line that I have in the state table corresponds to some logic that is built, and all of these would be. So, if I have S3 is there, then I would pick up all of that. So, that logic is picked up, this logic is picked up, and so correspondingly I would build something and I would send that to the respective input of the flip flop. Now, inputs have to be sent to 7 different flip flops, as opposed to earlier I had to send inputs to 3 different flip flops. But it is true that I need to compose the logic for the same number of transitions. In both cases the number of transitions is the same. Remember that by itself does not mean anything, because you can share logic. These are not distinct pieces of logic that you have. The point of optimization, logic minimization, of course, is that you want to generate the minimum area circuit by sharing logic. But these options need to be known to us. We do have at least the minimum number. So, we have a range of choices. One is the minimum number of bits, other is the one hot encoding that hopefully is the maximum number of bits. You do not need more than that many number of bits, because some of those may be redundant perhaps. For a particular encoding, you could choose any number of bits between log n and n, and there may be an argument in its favor. But the simpler treatment, of course, is these two extremes, the log n and the one hot encoded. Let us first understand, even before solving this, what are the possibilities I have. A brute force search could be that you generate all the encodings, synthesize circuits from each of them, and just choose the minimum area circuit. Is not a good one? How many encodings are there for an n state FSM? Can we precisely capture this number? It's binary encodings, can't be that hard. 2 raised to power n? Can we be more precise than that? Why 2 raised to power n?
Yeah, should be 2.
If I have some such logic S1, S2, S3, how many encodings would be there? It's 2 raised to power n if, is there a dependence on the number of flip flops we choose, number of bits I choose?
Yeah, 2 to the power n if we choose number of bits as n. Then it's like if it's less
If you
than
choose number of bits as n, but n is my number of states.
Yes, one hot encoding is 2 raised to power n, but no, that is fixed.
If you choose one hot encoding,
Yeah, then 2
then
no, then n
N states.
no. Any state can have one. I can choose.
one hot encoding, there's just one encoding.
No, but I can have S1 as 100 or 010 or 001. So I still have an option. So there is still an encoding option there.
Yeah, you can
Argue
you can
that
have
way.
that. Although when it translates to logic, they are all
Same.
probably equivalent to
Should
each other.
be.
Yeah, in that sense they are equal. But I have n states. How many choices are there? It is not independent of the number of bits you are choosing. There ought to be a dependence on the number of bits that you have chosen. Suppose I choose m bits, where I know what that m is. M is in what range?
N and log n.
Between n and log n, those are my choices. So, m bits I choose some number in that range. Now, how many possibilities?
2 to the power n.
2 to the power m, are we sure? So, if n was 8, if I had 8 states, then I would use 3 bits, suppose 2 to the power 3 is 8. Do I have only 8 choices for encoding? No. That would make it easier actually if the number of choices were only the number of states, then it is a linear function, and I could actually use the brute force method. It is just a very small number of possibilities. So, instinct should tell you that it should be a large, there should be an exponential somewhere, but where would that be?
If we have 3 bits, then 8 states can be captured using those 3 bits.
N.
But every state can be assigned any number from those.
It's a combination or permutation,
8
something.
bits.
Right.
So
If I have n states, how many possibilities do I have for the first one? 2 power n. 2 power m. Yeah.
yes, sorry. 2 power n.
They are independent things, remember, they are, we have to make the choice of what m is. So, m is not derivable directly from n. That many choices for the first state. Once you have made this, how many choices for the second?
2m minus 1. Like C. Combination, I think, not permutation.
That should be,
Then minus 2 and 1 up till 1.
then what, until?
N. Minus n.
Minus 1.
It is not exactly, but it is something like that. You started with minus 0, so minus n minus 1. Some such expression captures the number of possibilities. Of course, you can for the minimum value of m, you can substitute it and you can see that it is an exponential function, which is 8 times 7 times, yeah. Are we convinced that this is an exponential?
Yes, it is an exponential.
What is the proof that it is exponential?
It's a factorial kind of thing.
It is a factorial function, right. So,
Permutation, not combination. I was
so factorial is factorial exponential in n, is n factorial exponential in n?
It is, right? No?
Why? Yeah, I'm asking.
Is it plot and factorial the graph?
The graph looks like that, so somehow it's like a cup. Informally, these are cup-shaped graphs, and therefore one ought to be equivalent to the other. Is that a precise mathematical argument you are giving? It's not so hard to prove that n factorial. Actually, there is a precise. I'm not sure. There is an approximation for n factorial called Stirling's approximation, where the function looks something like n to the power n. There is, so n does appear in the. There are some other things. It's not exactly, of course, n to the power n, but it's not so hard to prove that n factorial ought to be at least exponential. You can show that.
We can break it down n factorial to n into n minus 1 up till 1, and then if we just ignore the constants, then it's basically n multiplied n times, so it comes n power n.
What? If you ignore the constants, everything is a constant?
No sir, like we are doing n times n minus 1, then n minus 2. So if we ignore this minus 1, minus 2, these are.
If you ignore all of those, then you have a totally different. Who says that every constant can be ignored in this way? If you have some function of n plus a constant, then you can ignore the constant. A constant is not always to be ignored in that way, although I appreciate the insights that may come up from it. It should lead to a clue that it is probably exponential. You can easily show that this ought to be worse even if you can't derive that closed form exponential. You should be able to prove, for example, that this is greater than 2 to the power n. Is it obvious from this expansion? Each of these guys is greater than 2 if you leave out this. So, there are n terms here. Yeah, not hard to see that this should be an exponential function. So, there is no question of generating n factorial encodings and generating circuits out of each of them and then checking which one it was. Although if it was linear, like if it was n, then that might have been a possibility. Okay. But with that background, let us look at one FSM encoding strategy that targets multi-level logic. This discussion is taken straight from that paper. It is an old paper, but it is selected for analysis just because there are some interesting concepts there that anticipate the effect of later optimizations. Okay. Later means whatever decisions we are going to be taken now are going to be subject to logic optimization that is happening later. We are not going to do that optimization as part of this process, and yet we can prepare the inputs for that optimization in a way that that optimization is able to find common terms and so on. That is the objective here. It is a nice way of estimating. These are estimates that we are making, but it is what we will go through in this argument is a concrete example of estimates of essentially literal counts. What we want to optimize is a literal count in that Boolean expression, but problem is that the Boolean expression is not there. At this time, the final Boolean expression is not there. In spite of that, we would like to anticipate what happens in the later stages, which is a little tricky, and therefore a little bit of a more concrete example might help us in quantifying those estimates in some way. That is what we will go through in this algorithm. So, objective of course is to minimize the expected gate count in the implementation when the implementation is not there. You do not want to actually implement it, but you want to argue at a logic level, if I did this, then this kind of logic is likely to be output, and those kind of opportunities the optimization tool is likely to extract, and therefore this is better than that. That kind of an argument is made here. For that, let us first introduce some typical optimizations that are actually happening in the multi-level logic optimizer. This will formally explore later on in the last stage of this course how the logic optimization tool works, logic synthesis mechanisms. But the principles are of course known principles. There is an idea of factoring. If you see something like this, right, b occurring, the same variable occurring in a complemented way or in an uncomplemented way in multiple terms like that, then I can extract out a common factor. Why is this a good idea? What does this optimize? Optimizes the number of gates. Our approximation of the gate count is literal. So, it reduces literal. I should be able to argue that it reduces literal, and therefore, I would do this. This does reduce literal. Right? I take a common b out, instead of 2 occurrences of b, I have 1 occurrence of b, and therefore, there is a reduction in the literal count. The rest of it does not change, but b's occurrences reduce, and therefore, the total literal count reduces. There of course, is a common sub expression argument here also. Of what nature? If I look at these two expressions jointly, I see that a plus b is a common expression, or it is a common sub expression, if each of them is a full expression. Because here that logic can be represented as a plus b times something times C e, and this logic can be expressed as a plus b times d e, and therefore, if I do that, a plus b turns out to be a common sub expression. Doing this would increase or decrease the literal count. Actually, I increase the number of expressions. I had 2 expressions earlier, now I have 3 expressions. Right. The gates is likely to be reduced, just because you see that there is some common computation that was taken out, that translates to number of gates, and that would reduce. You see that literal count, instead of a b occurring twice, a was occurring twice, b was occurring twice, at least as far as this part was concerned. We reduced 2 occurrences of a to 1 occurrence of a, reduced 2 occurrences of b to 1 occurrence of b. S was added here. So, anyway, overall you can see that such an exploitation of common sub expressions would lead to reduced literal count in whatever it is that I am implementing. A third one is a common cube. Occurrence of a common cube is identified as follows. Cube is a sort of a special case of the common sub expression, where there is just one product term in that expression. That is what we are calling a cube. In some ways, dealing with cubes is easier. Logic optimization, logic synthesis algorithms tend to work with cube, because it is an easier analysis. We will look at that analysis later, but finding a common cube is an easier evaluation than finding a general common sub expression that might be the sum of 4 different product terms, right. So, common cube, what common cubes are there in this expression here? I have an A e here, I also have an A e here. I can see that there is a common cube between these two, that is extracted out, and so u is extracted out, and I have the product of u with C and D. This is a little easier, because it depends of course on how you represent these things, but to take one expression like that, to one product term like that, and take another product term and find that there is a common cube between these two, you can see is an easier activity than take a general expression and some other expression and find that there is a common sub expression. Like this one is a harder analysis than this, because we are limited to just single product terms, not sum of product terms, at least the OR part of it is all gone, and we need to worry only about the ANDs.
One very tangential question.
Yeah.
The data structure point of view, doing the common cube approach probably simpler with a matrix implementation versus a graph. right? Because I mean,
Well, graph, we didn't talk about the representation yet, but,
But
so in the graph, what is the matrix, and what does the matrix have and what does the graph have? This is a general Boolean expression, right? So matrix means
in matrix I can keep these equations as a product of rows and columns. Maybe I'm not able to express what I'm saying.
actually the representation is totally non-trivial. What is a good representation is not obvious from here, but what we are just arguing in principle is that limiting ourselves to one product term, the possibility of finding a common, what is common between those two product terms is of course a simpler version of the general expression where you have sum of product terms and two sum of product terms and you find what is common between the two. This seems to be a more restricted version of the everything that you want to do here you also want to do in the other one, but you also have sum of products. So, it is just a conceptual argument so far, but we will get to, because everything in the logic synthesis has to do with how well you represent these things.
Coming from the constant multiplication scenario. Here it is not obvious how we can represent it. But in case of filter designs and stuff where multiple constant multiplications are there in parallel, and then graph based representations are very hard to code in terms of reducing the logic. If you put it into a matrix form, like y equals to ax,
In certain specific kinds of computation, certainly more interesting data structures could be generated. Graph does suggest itself as an obvious way to represent, just because if you look at the netlist, it is like a graph, right? Yeah. But still, you have to do more, and there are. We should spend some time on the interesting representations when we get to the logic level. As of now, this is only a principal argument.
Do we do both of these optimizations sometimes? Common subexpression and common cube.
If you have a good algorithm for doing common subexpression, you are also doing common cube as part of it. Yeah, it's just that sometimes in the interest of simplification, but particularly in this algorithm, why we introduce these at this stage is that this algorithm tries to maximize the availability of common cubes, assuming that the logic optimizer is handling at least common cubes. If common subexpression, it is fine, but even if not common subexpression, if it is doing common cube, then it will try to expose the availability of common cubes to the logic synthesizer. That is the reason why we are talking about it here. Okay, fine. Let me stop here. We will get to the actual algorithm in the next class.
Sir, why we do this common cube actually if we have common subexpression?
No. If you have common subexpression, then you don't do common cube. But you could do common cube and not do common subexpression, because that is more difficult. It is still a reasonable logic synthesis tool that would do common cube, not necessarily common subexpression. The other thing to note is that this can be done well. An algorithm that identifies and exploits common cube can perform very well. Quality of that algorithm can be good. Common subexpression is a difficult problem. Common cube is not hard to, as long as you have all the expressions, every pair you can take and you can easily argue whether a common cube is there or not, what is the size of the common cube, right, in an optimal way. That is not very expensive, but the common subexpression is hard to do. Remember, a plus b is same as b plus a. That introduces significant complexity into the process of identifying the common subexpression. You will find that as part of your, I assure you, you will come across that difficulty and be convinced totally by the end of this semester that common subexpression is hard, but common cube is much easier to do optimally even.